If you took the time to study the previous slide for a little bit, then hopefully you have some idea of what's going to be happening here. In the last lesson, Mrs. Milburn showed us how the angle in a circle can be related to the angle in a right triangle. If we have an angle in standard position, it's terminal ray coming out through the circle at the point xy, and we drop the perpendicular from xy down to the x-axis. Voila, we have a right triangle. The side that is opposite the angle is now the y-coordinate. The side that's adjacent to the angle is now the x-coordinate. And the hypotenuse of the triangle is actually the radius of the circle. So now we are able to redefine our trig values. The sine of theta, instead of being the opposite over the hypotenuse, is now the y-coordinate divided by the radius. Cosine of theta is still the adjacent side length divided by the hypotenuse, except now that's the x-coordinate divided by the radius. Tangent of theta is still the sine of theta divided by the cosine of theta. But instead of being opposite over adjacent, it's now the y-coordinate divided by the x-coordinate. In a unit circle, the radius is always 1, which means that the sine value is just simply the y-coordinate, and the cosine value is just simply the x-coordinate. We do not always have to have a unit circle. This is just a convenient circle with which to work. We can have a circle with a radius of 56 if we feel like it. Mrs. Milburn also emphasized the need to learn the trig values at the various quadrantal angles, and also that these quadrantal angles can be labeled in terms of pi. So all the way around the circle is 2 pi, once around the halfway around is 1 pi, 90 degrees is the same as pi over 2, 180 degrees is the same as 1.5 pi. Today we're going to extend these quadrantal angle values that you're supposed to know to include trig values, the exact trig values for 30, 60, and 45 degree angles, the ones that we studied in lesson 6.2. Time now to turn to the tables, which I hope you were able to print out. If you are unable to print a copy of the table, it won't take long. Just put it in your notebook. You'll need 5 columns and enough room in your notebook for 8 spaces down. I'm going to move this up, take the title out so that I can fit all the rows across. Okay, the table's been organized to help you memorize it. So we're going to start with 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180 degrees, and 270 degrees. Now these 5 above the line are either all in the first quadrant or surrounding the first quadrant. These other 2 quadrantal angles are sort of separate. Okay, theta in radians. So, we know that 180 degrees is the same as pi. And 270 degrees is 1.5 pi's. If 180 degrees is pi, then 90 degrees is half of a pi. 45 degrees would be half of 90, so that would be a quarter of a pi. If pi is the same as 180 degrees, then 60 degrees is a third of 180, pi over 3. 30 degrees is going to be 180 divided by 6, or pi over 6. And 0 degrees is still 0 pi. Okay, the sine values. And I'm just going to fill these in. The sine value for 0 is 0. Cosine value is 1. Tangent value is the sine divided by the cosine. The sine value for 30 degrees is 1/2. It's coming from our special angle charts that we did. The cosine value is the square root of 3 divided by 2. So the tangent's going to be 1/2 divided by the square root of 3 over 2, which becomes 1 over the square root of 3, and that's very nice. But if you're a purist and can't have any radicals in the denominator, then this becomes the square root of 3 divided by 3 when you rationalize the denominator. 45 degrees. The sine value is the square root of 2 divided by 2. Cosine value is the square root of 2 divided by 2. Tangents, the sine divided by the cosine, which of course comes out to be 1. 60 degrees. Sine value of a 60-degree angle is the square root of 3 divided by 2. Cosine of a 60-degree angle is going to be 1/2. Tangent will be the sine divided by the cosine, which is the square root of 3 over 1, which is going to be square root of 3. 90 degrees, the top of the circle. The sine value at the top is 1. Cosine value, right over the center of the circle, the cosine value is 0. So the tangent is the sine divided by the cosine, which is undefined. And these two quadrantal angles, theoretically, you already know. Pi all the way over to the left of the circle. The sine value is 0. The cosine value is -1. Tangent is 0 divided by -1, 0. 3 pi over 2 down at the bottom of the circle. The sine value is -1. Cosine value is 0. So the tangent is sine divided by cosine, undefined. Please take a moment to look over the chart, especially the sine and cosine values, and see if you notice any patterns. One pattern I was hoping you would notice is that the sine values going down are the same as the cosine values going up this way. They're the exact reverse of each other. And that's going to always be true for a very good reason. The sine of an angle is the same as the cosine of its complement. So the sine value for a 10-degree angle is going to have to be the same as the cosine of an 80-degree angle. In fact, in the old days, they didn't even bother to print the cosine tables. If you wanted to know the cosine of a 50-degree angle, then you looked up the sine value for its complement, sine value for the 40-degree angle, had to be the same thing. So that's one pattern that might help. I was hoping you might notice that a number of these had divisors of 2. We have the square root of 3 divided by 2. We've got the square root of 2 divided by 2. We've got 1 divided by 2. We can actually extend this pattern. Square root of 3 divided by 2 is the square root of 2 divided by 2. And 1/2 is really the same as the square root of 1 divided by 2. Will that work for 0? Would this be the square root of 0 divided by 2? We don't often think of it that way, but it is possible. So the sign values going down now are the square root of 0 divided by 2, square root of 1 divided by 2, square root of 2 divided by 2, square root of 3 divided by 2. Will this one be the square root of 4 divided by 2? Well, the square root of 4 is 2, and 2 divided by 2 is 1. So yes, we could write this as the square root of 4 divided by 2. This would be just going the other way. Square root of 4 divided by 2, square root of 3 divided by 2, square root of 2 divided by 2, square root of 1 divided by 2, square root of 0 divided by 2. It's a little awkward, but it's a very helpful pattern in getting us to memorize these. And yes, you are supposed to memorize these. If you are planning on taking AP Calculus next year, it's one of the prerequisites of the course. They're assuming that when you come into calculus, you are bringing with you in your brain the trig values for the special angles. I really only need to memorize sine and cosine because you can always then get the tangent values. And on the AP Calculus exam, more than half of it's without a calculator. So you're going to have to bring them in your head. Another possible way to help remember them is illustrated on the next slide, please. So if you'll check it out.